Welcome to final VSc Statistics students. In this lesson, we discuss the comparison of the variance of the sample mean in proportional and optimal allocations. In the previous class, we have discussed and we have compared the variance of the sample mean, that is variance of y bar n, in simple random sampling, that is random. We have considered variance of y bar n random. It is compared with variance of y bar st, variance of the sample mean, stratified sample mean, in the proportional allocation, in the stratified random sampling. In the stratified random sampling, we have two techniques: proportional allocation, optimum allocation. Two kinds of techniques we have, in which the proportional allocation, it is compared with random, simple random sampling, that is without replacement. In that technique, without replacement is more efficient than with replacement. Therefore, we have considered without replacement technique, and from which we are comparing the proportional allocation. The proportional allocation with the variance of the sample mean in simple random sampling, that is random. So variance of y bar n random and variance of y bar st proportion we have compared. Now in this lesson we compare another two particular techniques, that is proportional allocation versus optimum allocation. These are the two kind of techniques we compare here. The variances of the sample mean, which are going to be compared for these two techniques, and then finally we compare all the three techniques. Right? So now we take this two particular techniques. We compare. How do you consider? I write the formulas of variance of y bar st proportional. What is the formula of variance of y bar st proportional? 1 by small n minus 1 by capital N multiplied by summation I is equal to 1 to k pi into si square. That is the formula of variance of y bar st proportional. Then what is the formula of variance of y bar st optimum allocation? Optimum. It is 1 by small n summation I is equal to 1 to k pi si the whole square minus 1 by capital N summation I is equal to 1 to k pi si square. This is the formula of variance of y bar st optimum. So these are the formulas of proportional allocation, optimum allocation, the formulas of variance of sample mean y bar st. So now how to compare these two formulas now? Which one is less than of comparing the other one, and which one is less and which one is more? How to compare these two? For which I consider I subtract these two to compare and to know whether which particular variance is less. So I take the part of the subtraction, variance of y bar st proportion minus variance of y bar st optimum. So this I consider. Variance of y bar st proportion minus variance of y bar st optimum, right? Which means this is nothing but this is equivalent to be, or I consider this is equivalent to be 1 by small n minus 1 by capital N into pi si square minus of this, right? 1 by small n summation pi si whole square minus 1 by capital N summation pi si square. So now we separate this. This is equivalent to be this. So what is this? This is variance of y bar st proportion minus variance of y bar st optimum is equivalent with this. Now we do separate. We separate the terms and we simplify the formula. Is equivalent to b. Now I am multiplying 1 by small n with summation pi si square. So it is 1 by small n summation pi si square. So summation always depends on 1 to k. You please remember. And here in this particular terms, right? Minus 1 by capital N into multiply with 1 by capital N. Summation I is equal to 1 to k pi into si square. Now minus of this term. These two are the separate terms, so we can simply write the formulas. 1 by small n summation I is equal to 1 to k pi into si the whole square plus 1 by capital minus of minus, this becomes plus second term. 1 by capital N summation I is equal to 1 to k pi into si square. Pi into si square. So now you see the relation. See 1 minus 1 by capital N pi si square plus 1 by capital N pi si square will get cancelled. So therefore we have the terms 1 by n summation pi si whole square minus 1 by n summation pi si whole square. Right? So if we consider this, if we can take common as 1 by n, and so that these are two particular terms we have left. So therefore this is, have you understand this? From this step to this step. Now I proceed further. So this is equivalent to b. This is equivalent to b. 1 by small n multiplied by summation I is equal to 1 to k pi si square minus summation I is equal to 1 to k pi si the whole square. Okay. I consider I have taken a common as 1 by n and summation pi si square minus summation pi si whole square. This is the term remains from this after cancelling these two particular terms. We have only these two particular terms, in which we have take a common as 1 by a small n, and so that summation pi si square from here and 1 by a small n into summation pi si whole square here. So now I consider here in this particular term what I consider. Let us consider summation pi si is equivalent to be s bar. So then this particular term is nothing but 1 by small n summation I is equal to 1 to k pi si square minus s bar whole square. S bar square. Okay. So if you recollect the formula of 1 by n summation xi minus x bar whole square can be written as 1 by n summation xi square minus x bar whole square. 1 by n summation xi square minus x bar whole square. From this I write directly as 1 by n summation pi into si minus s bar whole square. This particular term we can write as 1 by small n summation pi into si minus x bar whole square. Don't compare with this small n. You compare with capital N inside that value. What is capital N there? In pi we have small n I by capital N. If you take that particular term, this will be true. Okay, in that fashion, 1 by n summation xi minus x bar whole square can be written as 1 by n summation xi square minus x bar whole square. So if you have any doubt, you can compare with, you come back with the comparison. So now I am doing here. So this is, I am considering summation I is equal to 1 to k. Summation I is equal to 1 to k pi into si minus s bar whole square. Take this particular term. This is square it. Square and take the summation. Summation I is equal to 1 to k pi into si square. A square term, first term, minus summation pi into s bar square okay, not minus, plus b square term, s bar square term, plus summation pi into s bar square. Summation always runs on I equal to 1 to k, plus minus 2 into summation pi into si into s bar. Okay, si into s bar is equivalent to b. So this is summation pi sa square, leave it as it is, and plus s bar square is a constant. S bar square is a constant, so we can take it outside. And summation pi is summation ni by n, summation ni by n, which is nothing but 1. Summation ni divided by capital N, summation ni capital N by capital N, 1. Summation pi is 1. So right here, summation pi is equal to summation ni divided by capital N, or I can write here in this fashion. So n is constant, I can take it outside, 1 by n, summation ni. What is summation ni? It is capital N, so is equal to 1. So therefore s bar square into summation pi, it is 1, minus 2 into, this is s bar we can take it outside, 2 into s bar multiplied by summation pi si. What we have considered pi si, summation pi si, s bar. That is what we have considered s bar. So hence it is summation pi si square plus this is s bar square, this is 1, and minus 2 into s bar into s bar, s bar into s bar square, minus 2 s bar square plus s bar square. So hence it is equivalent to be summation pi into si square minus s bar square. Have you got this value? These two values, summation pi si square minus s bar whole square. So summation pi si square minus s bar square can be written as summation pi into si minus s bar whole square. That is what I have written here. Have you understand this? I repeat again. So you see here, I have considered this summation pi into si minus s bar whole square, where s bar I am considering. S bar is equal to, I am considering summation pi si. Whenever I write summation depends on I equal to 1 to k. So I have considered summation pi into si minus s bar whole square. I am proving that it is nothing but this. This is nothing but this. So summation pi into si square, summation pi into s bar square, summation pi into 2 multiplied by minus summation pi into si into s bar to a term. So here s bar square is a constant I have taken outside. You leave this particular term. S bar square is a constant I have taken outside. Summation pi is nothing but 1. That's what we have proved. It's 1. So therefore s bar square. And this is summation pi si multiplied by s bar. S bar is a constant I have taken outside of summation. So 2 into s bar multiplied by summation pi si. Right? So summation pi si is nothing but s bar. So s bar into s bar. So 2 s bar square. Minus 2 s bar square plus s bar square, so minus s bar square. So summation pi si square minus s bar square, that is what the result. So summation pi si square minus s bar square can be written as summation pi into si minus s bar whole square if s bar is equal to summation pi si. If you consider s bar is equal to summation pi si, you remember, if you consider s bar is equal to summation pi si, I is equal to 1 to k, then this will be true. So therefore, why we are proving this? You see why this is required. Come on, tell me why this is required. This is required to prove that this term is greater than 0. Now you see this is a term square term. Here it is not possible to prove it whether it is greater than 0 or less than 0. The quantity, how this quantity would be, we cannot say. So now that is the reason why we have converted in this particular term. This term is observed small n, it is always greater than 0. Pi, ni by n, ni is always greater than 0, capital N is always greater than 0. So both terms are greater than 0. Why? They are units, number of units. So therefore, small n, number of units, sample size is always greater than 0. And Si minus S bar, whatever the values of Si and S bar whole square is always greater than 0. Summation is always greater than 0. So therefore, this term is greater than 0 for all the values of small n, capital N, capital N, etc. And S minus S bar whole square, it is always greater than 0. So therefore this is greater than 0. What is greater than 0? This is greater than 0 means variance of y bar s t proportion minus variance of y bar s t optimum, it is greater than 0. Now I am writing that. So therefore this is greater than 0. This is greater than 0. Do you agree with me? Since this is greater than 0, this is greater than 0. Which implies that, which means this is variance of y bar s t proportion minus variance of y bar s t optimum. If this is greater than 0, therefore which implies this is greater than 0. So this is greater than 0, which implies variance of y bar s t proportion is always greater than variance of y bar s t optimum. We have to show in another fashion. What is that? This is greater than this. That is variance of y bar s t. It is always in the proportional allocation is always greater than variance of y bar s t in optimum allocation. Therefore we can state that. Which implies variance of y bar s t optimum allocation, it is always less than or equal to variance of y bar s t. We can write greater than or equal to variance of y bar s t proportional allocation. Let you call equation number 2, which means the variance of y bar s t in the proportional allocation, it is always less than or equal to, which has the minimum variance in the optimum allocation than in the proportional allocation, that is variance of y bar s t in the proportional allocation. Therefore variance of sample mean you have considered in the stratified random sampling, optimum allocation gives minimum variance than the proportional allocation. So therefore this is the result we have obtained by comparing the variances of the sample mean in proportional and optimum allocation. If you compare, if you read and if you study the variances between proportional and optimum allocations, obviously optimum allocation gives lesser variance, minimum variance than the proportional allocation and in the proportional allocation. So therefore this is the comparison between optimum and proportional allocations. Now you recollect. Now we recollect one result we have established in the previous class, that between random, simple random sampling, that is random, and proportional allocation, which means I write here the result as well. We have called as Roman number 2, Roman number 1 there. So here Roman number 2. So variance of y bar s t proportional allocation is always less than or equal to variance of y bar and random. We have considered this is Roman number 1. Recollect and observe and see and verify and study the previous class that variance of y bar s t proportion is always less than or equal to variance of y bar and random, which we have considered the first relation, and the relation between the simple random sampling and proportional allocation. Now you compare these two, that is proportion is less than or equal to random, optimum is less than or equal to proportion. Now you see this one and then this. Variance of y bar s t optimum is less than or equal to variance of y bar s t proportion, whereas variance of y bar s t proportion is always less than or equal to variance of y bar and random, which means A is less than or equal to B and B is less than or equal to C. Therefore A less than or equal to B less than or equal to C, which can be established from these two relations, that is from 1 and 2. You have to do these two relations to get the comparison between among these three particular relations. Then we have to do these two relations first, and then only we have to establish this kind of relation between these two, that is proportion random and optimum proportion. So which means in the examination if they ask the question, the variance of y bar s t optimum is less than or equal to variance of y bar s t proportional less than or equal to variance of y bar and random, then you have to do the procedure from first previous class. You have to start the procedure of previous class, the established relation between random and proportional, and then optimum and proportional, and then we have to say this one, that is we have to give your conclusion of that variance of y bar st optimum is always less than or equal to variance of y bar st proportionalization is always less than or equal to variance of y bar and random. So this is what the result we have to prove it. The variance of optimum is less than or equal to variance of y bar st proportion, which is less than or equal to variance of y bar and random. So therefore, optimum allocation, by if you compare these three relations, these three techniques, simple random sampling without replacement, which means it represents simple random sampling, and proportional allocation and optimum allocation, two techniques in the stratified random sampling. If you compare all three, then the variance in the variance of the sample mean in the optimum allocation, which gives the minimum of considering of comparing with the remaining two, that is of proportional allocation and in the stratified random sampling and simple random sampling, that is variance of y bar n. So therefore, optimum allocation gives the minimum than remaining two. So therefore, this is what the conclusion. It also can be written as in this another kind of fashion simply. So it is variance of optimum is less than or equal to variance of proportion is less than or equal to variance of random. In this particular sense also it may give, or another fashion, variance of y bar and random is greater than or equal to variance of y bar st proportion is greater than or equal to variance of y bar st optimum. That is also true. Obviously, if A is less than or equal to B less than or equal to C, then obviously C is greater than or equal to B greater than or equal to A. So that is the kind of relation we know in mathematics. So therefore it is easy, and if you prove this, if they ask in the examination variance of y bar st random is greater than or equal to proportional is greater than or equal to optimum, then also that also can be proved with this particular result. You prove in the fashion that variance of y bar st optimum is always less than or equal to variance of y bar st proportion is always less than or equal to variance of y bar and random. This is what the relation between variance of the sample mean between or among the three particular relations. Among the three relations, optimum allocation, proportional allocation in stratified random sampling, and with the simple random sampling, that is simple random sampling without replacement technique. We have compared the variances of these three, in which optimum allocation provides the minimum variance, therefore it is more efficient than these the remaining two techniques, that is proportional allocation as well as in the simple random sampling. Simple random sampling, stratified random sampling, we can also give the conclusion that stratified random sampling gives the more efficient, it is more efficient than the simple random sampling. That's one conclusion we can give. Stratified random sampling is more efficient than simple random sampling. As well as now, if you compare in the stratified random sampling two techniques, optimum allocation and proportional allocation, with the simple random sampling without replacement, and of course in the simple random sampling with and without replacements which are compared, and in which we have explained that, and we concluded that without replacement SRS WR, which gives the more efficient minimum variance, hence more efficient than the with replacement technique. Now here we have entered two techniques, proportional and optimum allocation. We have established now the relation between optimum, proportional allocation and simple random sampling without replacement. You remember, always we are comparing with the simple random sampling without replacement. The technique. That is simply we are specifying that simple random sampling. So simple random sampling, random RAN, we have specified for that. So now we again compare three particular techniques, optimum allocation, proportional allocation and simple random sampling, among which the minimum variance is provided by the optimum allocation, therefore it is more efficient. So optimum allocation is more efficient than proportional allocation and as well as simple random sampling. Hope you understand. This is the kind of comparison between the variance of the sample mean among these techniques, optimum allocation, proportional allocation and simple random sampling. Thank you.